All right, so here what we are doing is we are setting up, practicing setting up a reaction table. So what this is going to help us to be able to do is by setting up a reaction table, we can take initial concentrations of reactants and we can determine, as long as we are given the equilibrium constant Kp or Kc, we can determine what the equilibrium concentrations will be. So a reaction table, or you may hear it referred to as an ICE table. There's the I, initial, C, change, E, equilibrium. An ICE table will help us to take initial concentrations, predict what the change will be, and then use math to find what the equilibrium concentrations are. Okay? So here we have a table, and they want us to complete it. So we're not doing the math here. We're just practicing setting it up, setting up our ICE tables, or they call them reaction tables. So all we need to do is just fill in these values. So let's take this table. Let me make it a little larger so that we can write in it. Okay? And let's see what information we have here. We have a 500 milliliter flask filled with 1.7 moles of SO2 and 1.5 moles of SO3. So we are starting with 1.7 moles of this and 1.5 moles of this. This reaction now becomes possible because this will decompose to form this in oxygen, and the oxygen will react with this to form that. Oh, the question is, how do I fill my table? Well, here in this table, we have concentrations. That I stands for initial concentration. C stands for change in concentration. E stands for equilibrium concentration. Well, to begin, we're only given moles. But I know that concentration is equal to moles per liters, or unit volume. And so let's take this milliliter, this given volume, and convert it to liters. So if I want to find the concentration of SO2, it's equal to the moles of SO2, which is 1.7 moles, divided by the amount of the volume in liters that it occupies, which is 0.5 liters. The concentration of SO3 is going to be equal to the number of moles of SO3, the initial concentration, divided by the volume it occupies. And the initial concentration of oxygen is going to be equal to 0. How do I know 0? Because he says to start with, we only have sulfur dioxide and sulfur trioxide. That's it. No oxygen. Okay? So the initial concentration of oxygen is a big fat 0. Let's determine what the initial concentration of SO2 is. 1.7 divided by 0.5 gives me 3.4 molar. So 3.4. And the initial concentration of SO3, 1.5 divided by 0.5, that's 3. Okay? So what we have just found are our initial concentrations. Initial concentration of this, this, and this. Now, in order to predict what the equilibrium concentrations will be, we have to know what the change in concentration will be for each of our substances. How is the concentration going to change as this reaction goes forward? Now, notice that they say use X to stand for the unknown change in the molarity of O2. We're not told which way this reaction is favored, whether it's favoring the products or the reactants. But we are told that X should stand for the unknown change in the molarity of O2. Look at X. X is positive, right? What's O2? A reactant. So this is telling us that the concentration of O2 is going to increase by some amount, by some concentration, by some change. We don't know what that change is, but we're going to let X represent that change, and we know it's going to increase. Well, oxygen is a reactant. If the concentration of this reactant increases, then so should the concentration of this reactant. Okay? So, if X is positive for oxygen, it's also going to be positive for sulfur dioxide. But, look at the stoichiometry. For every 1 mole of oxygen that's produced, 2 moles of SO2 are produced. So we have to pay attention to the coefficients here. So this will actually be plus 2x. For every 1 mole of oxygen that's produced, 2 moles of SO3 will be consumed. So we have 2 moles of SO3 consumed. The sign is different because SO3 is a product. Okay? So what we've done is we are using algebra to represent the change in concentration. We don't know what X is. It's some amount, but we're going to solve for X eventually. So our initial concentrations were here. These concentrations will change. The reactants will increase. Product will decrease. And I'm using this to determine what sign to use for my reactants and products. Oxygen is a reactant, so it's going to be positive. All the reactants will be plus, and the products will be minus. And so if I want to know what the equilibrium concentrations will be, well, what I'm going to do is I'm going to add up these two values here straight down. So I'm going to total them up straight down, all my columns. So the equilibrium concentration is equal to 3.4 plus 2x. The equilibrium concentration of O2 is going to be equal to, what's 0 plus x? X. What is 3 plus negative 2x? It's going to be 3 minus 2x. Okay? And so this 3.4 plus 2x is going to be the equilibrium concentration of SO2. All we have to do is find out what X is, and we have it. We have that actual concentration. All we have to do is find out what X is, and we have the equilibrium concentration of O2. And the same here. If I find X and plug it in here, I have the equilibrium concentration of SO3. So that's the next step, but right now we're just, again, practicing setting up our ice tables to find X and then know the equilibrium concentrations. So very, very powerful technique and powerful tool.